Right Academy. Learn it, teach it, remember it. A binary search tree is a decision you keep making. At every single step, you ask one question. Is my key smaller or is it bigger? And that one comparison throws away half of what is left. Play a quick guessing game with me. I am thinking of a number from 1 to 100 and you ask higher or lower. Guess 50, I say higher, so the lower half is gone. Guess 75, I say lower. Every guess cuts the numbers that remain in half. So you corner mine in about 7 questions. And from 1,000,000 in about 20. But that halving has a cost. It only works because the numbers are sorted. Higher or lower means something only because everything left is smaller and everything right is bigger. Shuffle them up and higher tells you nothing. The matches scatter to both sides at once. Now you are forced to check every single one. So here is the real question. How do we store a pile of data so every lookup stays one of those halving games? A sorted list does let you have a lookup, but inserting in the middle means shoving everything over. We want the halving and cheap edits at the very same time. A sorted list gives you the halving, but its inserts are slow. We want the halving together with cheap inserts and deletes. The binary search tree is the structure that buys you both. Picture that guessing game frozen in place. The first number you would guess sits right at the top, the root. Everything smaller hangs to the left, everything bigger to the right, and each of those piles is itself a smaller guessing game. Here is the whole definition. It is not just that the left child is smaller than the node. It is that the entire left subtree, every node inside it, stays smaller, and the entire right subtree stays bigger at every node all the way down. That stronger version is what makes the magic work. Let us build one, inserting these keys in order. 50 comes first, so it becomes the root. 30 is smaller, so it goes left. 70 is bigger, so it goes right. 20 is smaller than 50, then smaller than 30, so it lands as 30's left child. 40 is smaller than 50 but bigger than 30, so it is 30's right child. 60 is bigger than 50 and smaller than 70. 80 is bigger than both, out to the far right. And there it is, a tidy, balanced little tree. Now let us check the rule by eye. At the root, everything on the left is under 50 and everything on the right is over 50. At 30, the left is under 30 and the right is over 30. Every node passes the test. So this is a valid binary search tree. And here is the payoff hiding in the shape. Read the tree from left to right and the numbers come out sorted. 20, 30, 40, 50, 60, 70, 80. A binary search tree is a sorted sequence, folded up into a shape you can search by halving. Searching is just that guessing game played on the tree. Start at the root and ask the one question. If your key is smaller, step left. If it is bigger, step right. If it is equal, you have found it. And if you fall off the bottom, the key is simply not there. Let us find 60. At the root, 50, 60 is bigger, so step right. At 70, 60 is smaller, so step left. At 60, the values are equal. Found it in just 3 comparisons. Now notice what we never even looked at. 30, 20, 40, the whole left half of the tree, and 80. That very first comparison threw away half the tree, exactly like guessing 50 in the number game. Each step down is one more halving guess. Now search for 65, a key that is not there. At 50 it is bigger, so go right. At 70 it is smaller, so go left. At 60 it is bigger, so go right again. But 60 has no right child, so we have walked off the bottom. 65 is not in the tree, and that empty spot is exactly where it would go. Insertion is search that does not give up when it falls off the bottom. We already walked the path for 65 and ended at this empty spot. So we plant 65 right there. Search found the home, and insert filled it. Let us check it. 65 is right of 60, so it is bigger, good. It is in the left subtree of 70, so it is smaller, good. It is in the right subtree of 50, so it is bigger, good. Every ancestor is satisfied automatically because we only stepped where the comparisons forced us. The path itself is the proof. One subtlety to hold on to. The order you insert keys decides the shape you get. Insert 50, 30, 70, and you get a balanced fork. Insert 30, 50, 70, and you get a leaning tree instead. Same keys, same valid rule, but a very different shape. Here are the 3 operations written down. Search just walks down, comparing as it goes. Insert is the same walk, planting a node where it falls off. Delete dispatches on how many children the node has. Let us watch them run on a little tree. Search, then insert, then delete, each line lighting as it goes. Deletion has exactly 3 cases, and they get harder in order. Case 1, the node is a leaf, so just snip it away. Delete 20 and 30 simply loses its left child. Case 2, the node has a single child. Promote that child up into its place like pulling a bead from a necklace. Case 3, the node has 2 children, and that is the hard one. 2 subtrees beneath, and only 1 slot above. So what value can take that slot? It must be bigger than everything on the left and smaller than everything on the right. So it sits exactly between the 2 subtrees. We take the smallest value on the right, the in-order successor. You find it by walking left as far as you can. So it has no left child, a node we already know how to delete the easy way. Now let us delete 50 by hand. 50 has 2 children, so we hunt its successor. Step into the right subtree. Then walk left as far as we can, 70, then 60. 60 has no left child, so 60 is the successor. Copy 60 up into the root, then delete the old 60, an easy leaf. Read the tree out, 20, 30, 40, 60, 70, 80. The nearest neighbor stepped in, and the sorted order barely flinched. So why is it fast? Every operation is the same motion, walk one path, one comparison per node. So the cost is just how many levels you descend. Each level roughly doubles the number of nodes, 1, 2, 4, 8. That count how many times you can have a pile is the logarithm. We counted it, we did not just assert it, and the logarithm grows breathtakingly slowly. Multiply the data by 1,000 and the work goes up by only 10 steps. 100 items in 7, 1,000,000 in 20, 1,000,000,000 in 30. That right there is the prize. Now here is the dark secret. Insert keys that are already sorted, 10, 20, 30, 40, 50. Every key is bigger than the one before, so every key goes right. And right again, forever. You get a straight line, a linked list wearing a tree costume. Search for 50 and you visit every single node. The halving is gone. The cost is the count itself. This is the honest lesson. The rule guarantees correctness but not speed. A valid tree can be a fast, bushy one, or a slow, stringy one. And the whole difference is its height. A balanced height is the logarithm of the count. A degenerate height is the count. The fix is self-balancing trees. They do a little extra work on every insert, rotating nodes so the height stays near the logarithm no matter the order. You do not need the rotations today. Just know that when someone says a tree-based map is logarithmic, it is a balanced tree they mean. So how do you spot a binary search tree problem? Ask yourself 3 things. Do you need data kept sorted while it keeps changing? Do you need near queries, the smallest key above some value, or a range? Is the data dynamic and are the questions ordered? That pairing is the signature. If it is static, just sort once. If you only need exact matches, use a hash. but dynamic and ordered together reach for a tree. A handful of mistakes cause most broken trees. 1. Confusing the weak rule with the strong one. A deep node can beat its parent and still break a far-up ancestor. 2. Botching the two-child delete so a value appears twice. 3. Forgetting the degenerate case, testing only on a pretty tree. 4. Mishandling the empty tree and the root. Those boundaries are where trees crash. And here is the universal debugging move. Read the tree out in sorted order after every operation. If that in order read is not sorted, the rule broke. The values spill onto the line. And the first one out of place tells you exactly which operation went wrong. So here is the one model to keep. A binary search tree is a sorted sequence folded into a shape you can search by halving. Every operation is one walk down, one comparison per node, throwing away half each step. So the cost is the height. The rule keeps the walk correct, but it does not keep the tree short. Search, insert, and delete are all the same motion. The only hard part is the two-child delete. Swap in the nearest neighbor, then delete it from its easy spot. Keep it balanced and you search 1,000,000 items in 20 steps. Want to keep learning? Come find us at academy.rudewrite.com.